Record. Okay, so we're gonna do, this is like the fourth time this chapter 2 on the atomic theory. Okay, awesome. You can raise your hand if you want another printout about one more over here. Yeah. And Kyle, come around. Awesome, thank you. So this is kind of going off what I just said. This is one section in chapter 1, and this is the very last section in chapter 1. It's called phase change. There's some information, there's some tables, then there's some practice questions that are solved for you. So like try to do it on your own, but then it has the answer. So you know immediately if you got it wrong or right, and it tells you how to work it out. So on Monday, when I'm going to give you a handout that looks a lot like this. So you'll read it on your own. If there's any tables and figures, I'll give you a little note card. You can like summarize them in your own words. If you're artistic, you can draw pretty drawings. And then maybe I'll tape them up here. I'll tape everyone's up here and you can take photos. So again, one person's taking notes on chapter 1, but collectively we're on section 1, but collectively we'll have notes on all the sections. When you present to the group at the end, think about like explaining the tables and like the main points and any figures. Cool. So this is a nice example of what we'll work on Monday, but for chapter 2, not chapter 1. I did a little bit more grading. I'll slowly chuck away at the grading. If you're doing mostly great or great, I just like put the grade in. If it looks like you didn't do so great, I usually just like reassign it to give you a chance, because I would rather you learn the information and get the answer right than like make a bad grade. So just check your grades. If I reassigned it, then you can resubmit. No problem. Cool. Any questions about any assignments outstanding or not? Okay. Okay, so what I want to do today is by the end of the today, you should be able to distinguish between these 3 words. They're all like pretty similar and they can get a little bit confusing, but they do have different meanings. So shells, subshells, and orbitals. Again, all having to do with atoms and the periodic table and electron configurations. So you should be able to understand the order in which subshells are filled with electrons, and the periodic table is our guide with how they're filled. I'm also going to show you like a cool online tool that you'll have access to pretty soon. Determine how many electrons are in each subshell, that's a hard word to say. And write the electron configuration for a given element. So some of these things, there is a quiz that's going to open up at the very end of class today. So there will be a quiz. So things that I've covered in the last 3 lectures and today's lecture will be on that quiz. Yes.
What's the quiz do?
Sunday at midnight. It's 10 questions and they're 1 point each. So the last quiz, I do like short quizzes. The last quiz, it was nice because it was short. The only problem is when a quiz is short, then that means that they're 2-point questions. And so if you miss 1 question, you like make a B on it. I don't like that. So the quiz is 10 questions, they're 1 point each. Cool. And there's 3 true false questions and the answer is true. So there, you got 30 points.
So every true false question.
Usually, that's a pretty good, we're not trying to trick you. It's like trying to like repetition is gold, like just trying to repeat things and get it in your memory. Okay, so yes, so there is a quiz. They're only 1 point each, so you should be able to miss 1 and still make a 90. And if all you do is answer the 3 true false questions and turn it in, then you get a 30, not a 0. And there's 2 other free questions, like what have you learned and what are you so confused about? So there you make a 50 just for not even knowing anything. Okay. Does that make sense? Any questions about the upcoming quiz? Okay. Oh, last one. Explain how atomic radius varies across across and down the periodic table. And this last point should sort of help explain why electron subshells are filled the way that they are filled. But we'll get to that. Okay, this is a table, it's table 2.6.1. Oh, did I not have a definition in front of this? I thought I had a definition page. Nope, guess not. Okay. So shells are when we're drawing. So if this is our nucleus, when we draw a circle around it, that's considered a shell. And the shell, so if this would have one shell, and this would have two shells, this would have three shells. And when you're looking only, like if you ignore the middle, the metals in the middle, the shell, for the most part, corresponds to the row. So H, hydrogen has one shell, lithium has two shells, sodium has three shells. Every shell has subshells. Shell 1 only has one subshell, and it is the S. So if you look at the very top of the periodic table, there's hydrogen and helium. Those are both in the S shell, and that's the only shell, that's the only subshell, the S shell, in shell 1. If you look at the second row, you'll see that there's lithium and barium. That's going to be in the 2s shell, and boron to neon are in the 2p shell. And the 1s shell can hold 2 electrons, the 2s shell can hold 2 electrons, and the 2p shell can hold 6 electrons. So yes.
Do you recommend that we copy this down?
It would, you can either go into the file on your textbook and take a screenshot of it, or you can write it down. However you like to take notes and have things for, yeah, you can take a screenshot of it. Screenshots are nice, but you know, like, does anybody, like, before you go to the grocery store, you write down a grocery list, and then when you get to the grocery store, you don't have to look at your grocery list? Yeah, sometimes you still gotta look at the grocery list. You might forget like one thing. But usually if like you make a grocery list and you're like, sweet, it's in my head, the act of writing it down. But if someone just handed you a grocery list and told you to go buy all the things, you probably have to look at the list later on. Okay. The third shell has 3 subshells. And those subshells are called 3s, 3p, and 3d. And so this is where it sort of gets a little weird. The periodic table isn't perfect. Sodium and magnesium are in the 3rd row. They fill the 3s subshell. Aluminum through argon are in 3p. They fill the 3p shell. But scandium through zinc, they're in the 4th row, but they are the 3d subshell. And I've got a couple images, a couple slides later on that reinforce this. But so even there in the 4th row, this is called the 3d subshell. Okay, I'll stay over here. Then when we go down to the 4th shell, the 4th shell has 4 subshells, and they are 4s, 4p, 4d, and 4f. So 4s is potassium and calcium. 4p is gallium through krypton. Beautiful. Thank you. So potassium and calcium fill the 4s subshell. Gallium through krypton fill the 4p subshell. And then yttrium through cadmium fill 4d. And lanthanum and the last one fill the 4f shell. So the D and the F, they don't follow the row rules. Only these two, the first 2 columns and the last 6 columns, their shell is equal to their row. Okay, and so the way that we know how many numbers, does that not? It doesn't work on a screen, huh? Oh, yeah, it does, maybe. So the number of electrons per subshell is equal to how many are in these blocks. So these first two columns are called the S block. And actually, helium's a little weird. You could put helium over there because it's the S shell, but they put it over here because it's a noble gas. So these are, the S shell can always have 2 electrons. The P shell can always have 6 electrons. The D shell can always have 10. And the F shell can always have 14. So these number of electrons map perfectly onto the periodic table. So if you look at the periodic table, you can tell me what was the last shell that was filled. So cobalt, he's in the 3D area, so that he was a 3D shell was the 3D subshell was the last electron, or that last electron left. These are all P shells, so P subshell, so their electron went into a P subshell last. Any questions about that table and or how it maps onto the periodic table?
Can I ask a
Yes, please.
comprehension question for the class? Can everyone find calcium on your periodic table? Okay, can you guys, it's like Battleship. You guys all played Battleship before?
Oh, yeah.
Okay, you know, like if someone says A5, you like go to that column and you go 5 over. Periodic table set up that way. If you know where the S block, D block, P block, and F block are. So, like calcium, if I was playing Battleship and I wanted you guys to find calcium, what would I say it ends with? What's calcium's coordinates on the periodic table? 4s. Okay, so you start with the row that it's in. You see how calcium's 1, 2, 3, 4 rows down. So that's why Brody just said 4. And Brody, why did you say S? The S block. It's in the S block. You guys all find there's a little key on the left-hand corner of your periodic table. It shows you where the S block is. So it's 4 down on the S block. How far over on the S block is it? 2 over. So calcium's going to end at 4s2. It's like Battleship. Okay, you can find anything on the periodic table this way. Let's look at. Is it okay if I do one more?
Yeah, let's do one more.
So let's look at iodine. Okay, what's iodine's Battleship coordinate? First, count how many rows down it is.
5, P2.
5.
No.
P.
3.
5. So from helium, make sure you don't forget to count hydrogen and helium. That's a row on the periodic table. So I see 1, 2, 3, 4, 5 rows down. So it starts at 5. Okay, it's in the P block. How far over in the P block is it? P block starts here. 1, 2, 3, 4, 5 over in the P block. So it's 5P5. That's what it ends with. Okay, the only weird thing about this is you have to remember the D block. Even though it starts 4 rows down, the D block actually fills on the 3rd energy level. So if I was dealing with iron, even though it's 4 rows down, I'm not going to say 4D. It's 4 rows down, but D starts 1 energy level higher than the row that it's in. So even though it's in the 4th row, I'm going to say 3D, and it's 3D 1, 2, 3, 4, 5, 6. Okay, it's like that for the D and the F. The F block, which is down here, is 2 rows higher than you see it in. And I don't think they understand that the F block is actually here and not down here.
Yeah, it's like moved down.
Yeah, but there's like if you look at table.com, it shows you with it like spread out version.
Yeah.
Okay, so
what's one example from there? Like
let's take a cool one. Let's take uranium.
you are, or you in?
Just you.
Just you. Awesome.
Straight up.
Straight up.
Yeah, uranium it technically, it looks like it's way down here, but this is like a cutout. So technically the periodic table should be wider. I'll show you guys that maybe at some point.
I know, it's kind of like, it's almost like it goes like.
Really quick, this will really, and then I will leave you alone. I'm sorry, I'm jumping in. If you guys go to. Okay, the periodic table, in order to fit it on a sheet of paper, they dropped the F block underneath. This is what it should actually look like. You click wide version. Okay.
Nice.
It actually should look like that. It's like Alaska on the map of the US. Okay, instead of showing all of North America, they just grabbed Alaska and stuck it underneath. Alaska is actually not in the middle of the ocean. I don't know if you guys knew this or not. It's above Canada, right? So if you don't want it so wide, you just drop the F block underneath. So the F block is technically in the 6th and 7th rows. They just drop it underneath. So if we're doing uranium, it's in the F block. How many rows down is it? 7, but we subtract 2 from that number. 5. We're going to say 5F4. So uranium's electron configuration ends in 5F4. Okay.
Yay. Okay, any questions about battleship coordinates? We should play battleship. If somebody can find 14 copies of Battleship, then we can do it.
We could just set up periodic tables against each other and then
Oh. Okay, well, we'll add Battleship to Monday's reading activity. Okay. It'll be fine. Okay. So this is a figure in your textbook. It's figure, I don't know, because it's kind of not really showing the bottom of my screen. Our electron shells aren't really electron. Okay, let me go back one page. Okay, so there's shells, which roughly corresponds to the row on the periodic table, with the exception of the D and the F blocks. The subshells are the S and the P. And then we have what are called orbitals. And so every subshell that has an orbital, I feel like these are more or less interchangeable. The S, we're drawing it as like a sphere, and 2 electrons can spin around in that sphere, super happy. But the P shell, the way that we get 6 electrons in the P subshell is that there are actually 3 different orbitals, and 2 are spinning around in each one. And so they're oriented, they have a slightly different orientation. So the 6 electrons, like in our neon, that are in that P orbital, some of them are spinning like this, some like this, and some like this. So they're like not on top of each other. They have these different directions. Because what we'll talk about definitely on Wednesday is that electrons like to avoid each other. They've got negative charges, so they aren't attracted to each other. They repel each other a little bit, so they spin in different directions and trying to occupy different space. Yes? Always be 2 electrons. There cannot be more than 2. But so for instance, lithium, so the very first column, if we were in the same way that we wrote calcium is 4s2, potassium is going to be 4s1. So everything in that first row is only going to have 1 electron in its s orbital. Everything, so boron, aluminum, gallium, they're only going to have 1 electron in a p orbital. Calcium can have 2 electrons in p orbitals. Nitrogen can have 3 electrons in p orbitals. Oxygen has 4. So some of the orbitals can have 2. They can also just have 1 or 0. They can't have 3. Yes. Excellent question. And so continuing down, there's 5 d orbitals. So the way that we get 10 electrons in the d block is that there are 5 orbitals, and each of these orbitals can have 2 electrons spinning around in them. the reason the F block is 14 elements wide or atoms wide is because there are 7 different F orbitals that allow electrons to not interact with each other, to each have space and be happy in that F subshell. So this, I think, so there was the Bohr model says that electrons orbit like planets. And there's another one that says they're really in a cloud. So this kind of, if you stacked all these on top of each other and you tried to find the electrons, it's going to look like just a big cloud. They are floating around in distinct orbitals, but they've got this, like, they make a cloud space. Yes.
Those shapes that you guys are seeing are likely areas where you find the electrons, and they're not making those pathways, for example. Like, you guys look at those green images, the electrons aren't moving in like weird figure eight patterns. Those are the regions where you're likely to find the electron.
Yeah. Like, I don't know if y'all know what heat maps are, but like, it's like the likelihood, the proportion, like the likelihood that they are here. They may not be there, but 95%, if you have like an app tracker, you know how like apps track you? They're like 95% of the time they're in math class at 12:50. That doesn't mean that every single Friday you're in math class. It just means that more than likely you are there. Excellent point. Okay, so this illustrates what we were talking about earlier. So this map, this is a periodic table. But instead of having the element or the atom in each block, it's telling you this battleship coordinate. So for when we play Battleship on Monday, I will print this periodic table out. Okay, and it answers most of your questions. So you can check to see you got calcium right. So calcium 4s2, calcium, beautiful. And this is where it tells you explicitly that even though scandium is in the 4th row, it's the 3D subshell. And even though I can't tell what it's called, even though it looks like it's in the 6th row, it's the 5th D shell. Or even though it looks like it's in the 7th row, it's the 5th D shell. Oh, sorry. So actually this one has, every periodic table is just a tiny bit different. This one it's pulling out, there's a 5D1 and a 6D1 and then 4F1. So 4F1 starts in this 6th row. Yeah, so I'll print this one out so that you can look at the periodic table and then you can look and you're like, okay, 5S1, 6F2 when you play your Battleship. Does this help make sense what we explained like 2 slides ago? Yeah. Awesome. Okay, so the way that the reason why the periodic table is numbered by the atomic number. So if you go across the 4th row, it's 19, 20, 21, 22. That's how many protons each of these atoms have. But the reason why it's called the 3D shell and not the 4D shell has to do with the energy levels. And electrons are filled into these orbitals in a way to minimize energy. So this is, I think this is actually from a different textbook because I really liked it. But what it's showing is on the y-axis is potential energy, so increasing energy. And in here we have our S subshell and our P subshell and our D subshell and our F subshell. And it's oriented, so the x-axis is what subshell it is, so S, P, D, F. And it's oriented from their energies, from bottom to top. So the 1s shell has the lowest energy, so electrons always go there first. Then the 2s subshell has the second lowest energy, so for barium, its electrons go first in the 1s shell and second in the 2s shell. Then we fill the 2p shell, so kind of going across the periodic table. boron, carbon, nitrogen, oxygen, fluorine, neon, they fill this 2p shell. Then the next lowest energy is 3s, then 3p, then 4s, then 3d. So after 4s is 3d. So that's why that periodic table looks like that. So potassium, calcium, what's Sc? Scandium. So after we fill the 3s, then we fill the 3p. Then we fill the 4s. Then we fill the 3d. Then we fill the 4p. Then the 5s. Then the 4d. Then the 5p. And so you would think logically like 1s, 2s, 2p, 3s, 3d, 3p, but that's incorrect. It goes in this like zigzag pattern that follows the periodic table perfectly. So if you follow the periodic table, you'll know exactly which order the electron shells are filled. And this is how you write it. This is one way that's written. First 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d. And you can follow it along the electric periodic table or write it out. So on this graph, what has the lowest energy? 1s. And what has the highest energy? 5f. Okay, so that's that fifth row is going to be their electrons are added last. I wonder if there's a row 8. 1, 2, 3. Nope, awesome. Okay, so these blocks are a common way that people, so instead of drawing like a really awkwardly shaped electron that looks like a globe, people will draw a square to visualize how many electrons are in each one. So hydrogen has 1 electron in its 1s shell, and we write that 1s superscript 1, kind of like we did over here. Helium has 2 electrons, and they have opposite spin. That's what the arrow represents. This has 2 electrons in its 1s shell, so we write that as 1s2. So the 1 always corresponds to the row or the number of which shell it's in, and the superscript corresponds to how many electrons are in that shell. So on the previous one, there was just one red S ball, like one red S sphere. So the S can always have 2. Sometimes it only has 1. If that, it may not have any. Oh, I don't need the news. Okay, and then continuing, we can keep writing, we can keep drawing this out. This is another model, another way we can visualize atoms since we can't see them. Can't see atoms and electrons. You can write out nitrogen. It's got 2 electrons in the 1s, 2 electrons in the 2s, and 3 electrons in the p. So the way you would fully write that out, like not just the battleship coordinates, but the full complete electron configuration, then be 1s2, 2s2, 2p3. So if you went across the periodic table, if to get to nitrogen to fully write out the whole thing, you have to trace the whole periodic table. So you go through 1s, 2s, 3p. 1s2, 2s2, 2p3. Again, oxygen, both the S1 is filled, the 1s is filled, the 2s is filled, the first 2p is filled, and there are 2 more p orbitals that have 1 electron in them. Yes, question.
So I see that there's for nitrogen on the P block, it's all up arrows.
Mhm.
Can you explain why that is, or why is it all up arrows?
So I think it could be all down or it could be all up, but basically they're first, rather than have 2 electrons in 1 orbital going in opposite directions, those are still pretty close together. So instead 1 occupies each different orbital. That spreads out, that makes them the farthest apart they can possibly be.
I just want you to like this. So the electrons want to spread out as much as possible in the block that they're filling. Like seats at a concert,
Mhm.
you wouldn't want to, if you can, you don't know the people, you want to like space out as much as you can before you double up. So you see oxygen has no other choice but to start doubling up the P block. But it's gonna go spaced out, if it can first.
Yes. So I've got two more slides. I'm going to show you one activity that like makes you get it right, which is pretty cool, this online tool. And then I have a not quite a concert example. This might be the next slide. Okay, we're close. We're getting close. So again, there's a table in your textbook. So when we read on Monday, someone's going to get to have the joy of explaining this table to their neighbors when they read this in the group. But so again, if we're reading across the periodic table, this is our atomic number 1 through 10. Elements hydrogen through neon. And the outermost shell for hydrogen helium, the outermost shell is shell 1. For lithium through neon, the outermost shell is the second shell. And this is how you would write out their full electron configuration. 1s1, 1s2, 1s2, 2s1, 1s2, 2s2. So it includes all the previous electrons. All the way down to neon is 1s2, 2s2, 2p6. So if you trace, like if you drew a line all through the periodic table, that's how it would take you to get to neon. So you can look these up, which is the cool thing. You don't have to memorize them. You could look it up. When you look it up, if you do want to be able to understand what they're saying. So does everyone understand what these are telling us? The order of which the electron orbitals are filled. Okay, we'll get to some illustrations in just a moment. What's cool, so these get really long, like ridiculously long. Nobody wants to write all this out. And so we have what's called the noble gas configuration. So that far right column, those are our noble gases. And so what you can do is to simplify most of this, what you can do is take this, the preceding noble gas and put its symbol in brackets and then just write what precedes it. So this gets us very similar to this battleship coordinates. So instead of going through, like if you want to talk about rubidium, which is in the 5th row, instead of writing out the whole entire electron configuration, you go, what's the last noble gas? It's krypton. You'll put krypton in brackets, and then you just have to write the battleship coordinate. And that is like a legit, like scientifically sound way to talk about what electron configuration are. So for neon, instead of saying 1s2, 2s2, 2p6, we say helium, 2s2, 2p6. So that takes out all the 1 shells. The further you go down, this shorthand makes it a lot simpler, and it allows you to just focus on the outer shell. Again, when we read on Monday, one group is going to get the joy of this section, and you'll get to read about that in more detail, summarize it, and then explain it to your neighbors, the whole class. Okay, so this is, there's a million different periodic table versions out there. This structure is really elegant for organizing by atomic number. And they're also, because they have similar properties in similar rows, the columns have similar properties because of their electron configurations. So the far right, they're called noble gases. Their outer electron shell is full. They don't really like to, we're going to talk about this more in subsequent chapters. They don't really like to bond with anything. They just like to hang out on their own. So they're called our noble gases. Halogens have all of the F, fluorine, chlorine, bromine, iodine. They all have similar properties. They're called halogens. These are transition metals. They're electron, they're called transition metals because they're kind of like a hybrid. They kind of like look like some things, kind of look like a metal, kind of don't look like a metal. And also their electrons like to transition between levels, which complicates things. And then we have our alkali and our alkaline earth metals. So everything in a column has similar properties to other elements in its column. The gray block, there's one more. I feel like they call them like metalloids. I think they wanna call them metalloids. And sorry, it's in one of these printouts that's what I was looking for, because I don't include it there. I'll find it. We'll answer that question next week for sure, if not today.
Metalloids, but metalloids, we're gonna kind of.
Semi-metals. They're like. Some atoms behave very predictably. Like, there's only one or two options. Other atoms are like a little bit more ambiguous and they can have multiple charges. And so they get grouped into these like semi-metals and non-metals. We'll go over that more on Monday. Excellent question. And again, on your quiz today, if you don't want to ask a question in class, on the quiz today, there's a space for you to put things that you're still confused about this chapter, and we can make sure we cover them on Monday. Okay, so this again, so the way that we write that noble gas configuration, which I was talking about, which is the shorthand, is you find the noble gas that precedes that element, write that symbol in brackets, and then write the remaining electron configuration. So there should be a 1 right there. Potassium 4s1. Your yttrium would be xenon 6s2 4f14. So given this, if I gave you this configuration, kind of like the battleship game, if I give you this, you should be able to go point to go yttrium. And you can communicate with other scientists that that's the element you're talking about without writing the full long thing. Okay, so let's do our little battleship. We can write it like this. We can do our battleship coordinates. So just the very last one. So we've got lithium, oxygen, neon, sodium, and aluminum. Yes.
Would it be okay if they wrote the full configuration for half?
You want to? Oh, okay. So
Because I
take
think
3
it's
and write the full
practice.
configuration. The first 3.
That would be, yeah, that's good.
Yes. I'll print out some graphs next. I'll print out more. Yes. That November 5th. Okay, thank you for letting me know early. Okay, so definitely want to make it, definitely want to get you to go 4. Let me chat with Pat, figure out the best, because we are gonna have like the day where we're going to. I don't want you to have to like, before you go see that'd be a little unfair. You should have access to here. What you're gonna be done wired. Yeah, okay, because we've got 2 options. Either we can make set aside, or you take it, short, it's on a short day. Or, we can make it available on here. Well, I'll find out which one. I think the way this study works. Everything goes, yeah, so everything's on console, collection recording, slash slide. So I'm just giving you like an extra. Yeah. You can always go. If the network, as soon as you get the homework, you can still. You're like, I want to get the homework. The previous down for neon. Yes. Oh my God. Yes. Okay. All right. Four. Yes. You can, so this is like the shorthand, this is, as we were saying, this is like the battleship coordinate. You would write everything that was it. So in front of two, so what would come in front of it is you guys take the electron, so there's one electron here, one here, over here, one. Oxygen, you get oxygen, you have one is two, one. So this has so you could write. All of the preceding ones. So we have to write them. That's the long format. So I probably won't make you write them, but on the quizzes I will make you show me what to take the writing line out of my stuff. So you can, there's two, so these are orders that are kind of like our battleship coordinates and the coordinates. You can either add one and two in front of them. You can add helium and practice. And that's so.
Oh, yeah, I like you like that. What do you? Oh, how many? What is it?
Three to get to. Try.
Well, let's accept.
It would be two.
You guys remember this?
No. No, I mean.
One or two,
We're gonna,
two or
we're
two,
gonna start at about
56, 3 or 4. Three, like, what?
we were.
That's what we're doing.
So you go across this periodic table, you kind of ignore the name,
That's what it ends in.
and it will say the electrons. So
Do you any of the full configuration?
it's, that's what,
That's what it ends in. Right out.
the block is labeled to, to get there, we go through the one, so one S.
All the electrons up to.
What?
Saying that it ends with this. It ends with the same thing.
Beautiful.
So what you say, this is.
Oxygen, we go through one S, so we write one S two.
But then you say the wrong.
Two.
Oh.
It's wait.
Right.
Because I gotta see here.
Because, we don't have to write out every, there is the orbit. So kind of like, we're not. So you don't have to write one extra, you don't have to write every, just write it. It's, yeah.
Yeah. And what's this?
I can start at one S two, and then it becomes.
And then
Two
two sodium is.
Three, and then one.
So write down everything. That's the difference. So it's gonna end with this. And sometimes move this over.
One is two.
I forget how much years. I switched up.
One is two.
These ways, you just go to where.
Yeah, so remember recent students. Have to do before. Okay, so this is what again? Good, so you're right that. And this is.
Yeah, do it for-
Two. Okay, and then after the rest two I have.
And then.
And then N2. That's the entire configuration. So it ends in that, but fills every. There you go, say every single block and you're saying all the way out there. What's quick, let's get it, right? Just say one S two, one S two, six, four S two, any, three S two, four B six, five S. Just like a book, you gotta know what each line.
Everything.
You got it. Okay.
Yeah.
Yeah. I really.
Yeah.
And you can also create one something back. Okay, so. Do you need help?
Yeah, I think we went through it.
What are you trying to do right now? Sodium? Where are you at? Well, the first problem you have is your watch chart covering here. What, pyramid table? Oh, yeah. But where is? Where's two S two?
Yeah, it's easy to like.
Sodium? Two S two is where? That's two S two. Yeah, right there. Okay. What comes after two S two? Where am I in? Second row, what block is this? Block, I would say 2. Feet. How many elements are in the block? There's like 2d6. Because I need to fill, electrons have a role. Here at a table based off of where the electrons live. Okay, there's 6 electrons down here. So I'm filling every single electron here. And sodium. Because electrons.
The answers are in the table. I don't know if I have them on the slide. Or do I have them on the slide? No.
My electron bucket is the hot model for the electron.
But I don't know.
Why 8? Why 2? No, it's not going to. How many elements are in the first? Wait, how many are in the first rank? Reconnected. Wait a second. Wait a second. Second, 8. Here. Okay, so we have 1, 2, 3, 4, 5, 7, 8. Okay, how many electrons? Okay, and how many electrons? Wait, you're telling me about one more? Are you kidding? Where's sodium? And where's the O? S.
Together.
1. How many electrons are in the third shell? It's asking why you have these first. So these first model.
Second ring is the third one.
Five electrons. So that one should be 6, yeah. Yes. Yeah.
All good?
I think
Everyone. Okay, yes. How would you write? Not format what? Because there's no notes that's about it. So also. Okay. Okay. I have a little analogy that hopefully it will help I probably could have done this earlier, but I wanted to get through the content before I gave an analogy, just in case you didn't get there. So filling the D, so the D and the F shells, filling the D and F orbitals with electrons is kind of complicated. I showed you the energy graph earlier, which I think explains things really well. Kyle was giving a concert analogy, like, you know, you don't necessarily want to be near neighbors. I have a parking lot analogy, because I park cars at Alpine Meadows when it's wintertime. And I swear electrons are filled the same way we fill parking lots. So does anybody ever go skiing on Powder Day? Yes. Has anybody ever been to an event where there was a parking lot attendant telling you exactly where to park?
Yep.
Yes. Okay. So electrons, you can sort of think that like there is someone telling them where to go that maximizes like efficiency and energy. So your goal, you want to park like as close as possible. Or if you have a nice car, you might want to park far away so nobody hits your door. But if there's a parking lot attendant telling you where to go, you kind of got to listen to the parking lot attendant. Or, you know, you should at least like, you know, when there's like 1,000 cars that are all coming in at once. If it's a slow day and it's sunny and nobody's there, then you don't have to listen. But so like your goal is park as close as this venue. You're calling it a venue, like a concert venue. The parking lot attendant's goal is to establish an orderly parking lot structure. And they have this rule, like you know, their boss gave them a rule, start a new row when there are 8 cars in the outer row. So I've got this little analogy here. The first row kind of represents our 1S. The second row kind of represents our 2S and 2P. Third, 3S and 3P. And so I'll show you like the way that we fill electrons is kind of the way that you're writing these electron dot structures. Sorry, these electron configurations. So the first 2 cars come in, bam, we park them in the first 2 spots. And you can kind of imagine, you know, how we talked about earlier, they're going opposite directions. When these 2 cars leave, the first one can exit forward. The one that leaves has to like reverse. So 2 more cars come in. You're going to put them right there on the end. Like you're the attendant, you're going to put them right there on the end. Now people will know that knows where this row is. Especially if you can imagine it snowed and there are actually no lines on the lot. But the parking lot attendant knows where the lines are because they're familiar. And then you're going to add 3 cars. You're going to pull those 3 cars up, tell them where to park, establish the structure of the parking lot. Then you add 3 more cars. So the way this corresponds to what we've been doing is we have 2 in S1, 2 in S2, and 6 in 2P. Then we're going to add some more cars. First, we're going to first put the end caps on. This is like our 3S2. Now we have 3P3 filled the first row, 3P4. Sorry, 3P6. So we're slowly filling each of these rows in. We add 2 more in 4S. But then as soon as we have this 4S, what happens is you can like open up a new section. It's like, whoa, we're getting pretty far away from this venue. Nobody wants to be really far away from the venue. Nobody wants to walk that far. The parking lot attendant's like, hey, actually, I can get 10 more cars in this row. This is our 3D analogy. We can't, when we're filling up these electrons, if this is a Sharpie. This is our 1S, and this is our 2, sorry, this is our shell 1, shell 2, and shell 3. When this has 8 electrons in it, it can't really take 10 more. But when we add a 4th shell around it, this 4S, it actually makes space, and now you can get 10 more cars in there. And they're closer to the nucleus. So after we fill the 4S2, so after potassium and calcium, after we fill that 4S2, then we can go back and fill in the 3D. Because now there's space in this 3rd shell for more electrons. First, we fill each of the orbitals with one direction and then complete it with the rest of the 10. So now we're going to go back to the 4th shell, add our P electrons. Then we're going to open up the 5th shell, add 2 S electrons there. And now we have space for more P electrons, the Y through CD. Now we're going to go across fill in the p electrons. Go down to the 6th row, add s electrons, and then, but it's like, well, we're too far away from the parking lot. Let's open up some more parking spots that are closer to the venue. The venue in this illustration represents our nucleus. So everyone wants to park as close as they can. And so this would look like, if I go, this is, I think, like 70 cars. If we oriented it on, if we made a Bohr model of it, this is how those electrons would be arranged. There's 2 on the outer shell, and then we have 2 in our S1, 2 S2, 2 P6, 3 S2, 3 P6, 3 D10, 4 S2, 4 P6, 4 D10, 4 F14, 5 S2, 5 P6, 6 S2. And so this is how I've written it. I think it got cut off at the end. But so this, I've told you it's 70, it has 70 electrons, 70 protons. You can find 70 over there, it's yttrium. Yes, question. This one has 6 orbitals. So again, 6 orbitals, 6 shells. It has 6 shells.
Yeah, so I get that confused all the time. You can think of SPD as like shapes the electrons take within each shell. So like the first shell, you can see like Dr. Harris labeled that first shell there, like said number 1. How many different shapes, it's kind of a trick question the way I'm phrasing it, but how many different shapes are in that first shell? Just 1, right? Look at the first row in your periodic table. What's there? Just in S, right? It's just S. Okay, what about the second row on the periodic table? What 2 different shapes are in the second row? You see an S, which is lithium and beryllium, and then you go over to right and you see a P. And then the third one is what? S, P. But you remember how the D starts at 3? Not F.
Oh, sorry.
So it's 3D. There's 3 different shapes. Now the fourth one is S, P, D, and F.
This is what we wrote on that table, the very first table we started with at the beginning of the lecture today.
So as you go farther out in your rings, you get more shapes. And that means you can fit more electrons in each one of those shapes. Like the S can only fit 2 electrons, but the P can fit 6 electrons, and the D can fit 10 electrons. And then the F can fit 14 electrons. A lot of crazy info I did.
It's a lot of info, and so I included this caveat. So the main reason why they're offset, so the reason why this is 3D instead of 4D, is it's because that outer shell, to be stable, the outer shell never has more than 8 in it. So we've got the 2S, we've got the S's and the P's, that'll make 8. But we can't have 18 in the outer shell. We can only have 8 in the outer shell. So we add 4S. And then now that we've had 4S, it makes space for there to be more electrons inside, and now we can fill in the 3D. Okay. So this is the full written out electron structure for yttrium. This is why nobody really wants to do that. That's like so much writing. Right? So we can use the noble gas configuration to say, well, what precedes yttrium is xenon. We put xenon in brackets, and then it's 6s2, 4f14 to get to yttrium. Okay. So there is one more thing that happens. So have you ever been in a parking lot and the parking lot attendant told you where to park and then you moved somewhere to a closer spot? Yes. So electrons do that as well. So I gave you a trick question earlier. So silver, if you follow the rules for silver, it's gonna go all the way up. It'll have 2 in the 5S and 9 in the 4D. But actually, this one, it's gonna be like, hey, this is too far away. I wanna go over there. And so sometimes like electrons will move to a different shell to maximize energy. And so theoretically, it's 9, 4D9, 5S2, but actually in real life, where it's more likely found, 4D10, 5S1. So I wanted to, so the reason I emphasize this, it adds a level of complexity. I probably could have cut it out. All kind of anything and it's gonna do the same thing with silver. What's below? Where's the other? It's silver and gold both do that. Okay, so I wanted to show you there's this app that puts everything that I've said into play. If I can click the button, and you'll have access to this. So Kyle's gonna be gone for like 2 or 3 weeks. Yeah, I know, right? And so you're gonna have access to this, but I want to do a little demo. Like, there we go. So this is an online tutorial that you can use to practice filling in electrons, and it will tell you the electron configuration. Okay, so these boxes are ordered exactly the same way of a graph I showed you earlier. The 1s has the lowest energy, 2s has the second lowest energy, 2p is the second next to that one. And so what you can do is it's going to give you a periodic table element, lithium. And you're going to click, you're going to add electrons into the boxes, and it will write the electron configuration for you, and it will show you the Bohr model of where those electrons show up. So if I click lithium, the electron configuration is 1s2. So I put 2 electrons here, and 2s1. So I put 1 electron there. And then you click show total electrons. There's 3, and then you can check your work, and it says correct electron configuration. So this is how you can practice on your own. We click next element, beryllium. Where would I add 1 more electron for beryllium? 2s, beautiful. So I'll click that. Now I can see that my electron configuration is now 1s2, 2s2. I can check it, and it says correct. So you keep going through. Boron, we're going to add 1 more electron for boron? 2p1, check. Okay. So on Monday, I'm gonna pass out assigned readings. So anything, and I'll do a little quiz, and not quiz, but like a little hand show, and see what you're confused about, and whatever you're most confused about, you might get that assignment. Yes, question. This one? Okay, so there is a quiz. It's on Canvas now. 10 questions. You can take it. It's due by Sunday. Any questions before you go? Awesome. Have a great homecoming weekend. Thank you. What do you need?
I really don't want to pull it out. Have one? I did.
Want to do homework? Yes. Do Sunday midnight.
And then that's the adult.
This one is also due Sunday, I think. This is the homework. Yeah.
I don't really have a way of turning